then we will go ahead and get started. Like we said in the video from yesterday, this is part 2 of the notes. So we're going to look at more examples of systems you can solve using elimination. And then we're also going to identify types of solutions. We saw a little bit of that in the lesson we did on solving by graphing. But now that we've been doing all the solving algebraically with substitution and elimination, we're going to come back to what different types of solutions look like. So, before we actually, I was going to say before we go, let's review, but I remember there's a slide to do that. When we talked about the goal of elimination, the goal of elimination is to eliminate what?
One of the equations, one of the variables?
Yeah, it's to eliminate x or eliminate y. So you want to eliminate one of those two variables. The reason we want to do that is if you eliminate one of the variables, it's going to leave you with only one variable left, and then you're able to solve. In order to eliminate a variable, what needs to be true about the signs? The signs need to be
different.
Yep. And then we also said the numbers need to be
the same.
So we need something like -3 and +3, +10 and -10, something like that in order to eliminate. So keeping all of that in mind, in the lesson from yesterday, we saw a couple different situations. We saw systems where that's already true. You don't have to do anything. You don't have to change anything. You could just go and eliminate something. We saw examples where you might have to change the sign or subtract to have them be different signs so that something eliminates. And then the last example we did, we saw systems where you might have to multiply one of the equations to make something eliminate. This is the last example, or last type of problem we're going to look at. I've got this system here, and we're going to solve using elimination. Now, if I'm just looking at it the way it is anything going to eliminate if I go to add those equations?
No.
How do you know that?
Because none of the numbers are the same.
Nice. None of the numbers are the same. That also means if I go to subtract, nothing's going to eliminate either, because you've noticed the numbers are different. In the lesson from yesterday, we saw, okay, that's not a big deal. We can just multiply one of the equations to make something eliminate. Do you see a number we could multiply one of these equations by to get x to eliminate?
No.
Why not?
Because there are no numbers that you can multiply to get them to the same number.
Yeah, if I'm looking at that smaller number, there's nothing we can multiply 3 by to give you a 4. What about the y's? No. There is something you can multiply 4 by to get 8, but that's not a variable. We're not trying to get those numbers to eliminate. This does not mean that all hope is lost. It just means that instead of only multiplying one equation, we're going to have to multiply both equations. Now, in order to do this, there are a lot of different ways you can use elimination to help you solve this. We're going to start off by picking which variable we want to eliminate. There's no right answer to that. We can choose x to eliminate, or we can choose y. I'm going to have you choose first.
I guess 4 and -3.
Okay, so we're going to have our x's eliminate. We've said since there's no way for me to multiply one equation, I'm going to have to multiply both equations. And there's a pair of numbers you can use here so that after you multiply, you end up getting the same number. Do you see what two numbers we could multiply here?
Yes. Be 3 and 4.
Where did those numbers come from?
Nowhere.
I mean, I see somewhere they came from. Why did you choose 3 and 4?
Because you can do 4 times 3 to get to 12, which is also 3 times 4.
Yeah, so really what we're doing is we're just kind of switching around those numbers because you're using the fact that 3 times 4 and 4 times 3 give you the same thing. Now, sometimes we also have to worry about the signs. So you had noticed earlier the numbers are different. So we had to multiply by numbers to give us the same number, 12 for both of them. Are our signs different right now?
Yes.
Yeah. So that's helpful. It means we don't have to worry about changing a sign. If it had been something like 4x and 3x, then we would have needed a negative sign somewhere. So it could have been a -3 or a -4, but you would have had to add in a negative sign to make them different. Once we've got this though, we've got it all set up, let's go ahead and multiply. When we multiply this first one,
Be 12x minus 9y equals -12.
And then the second one,
Be -12 plus 20y equals -32.
There's something there I want to go back and...
Or -12x.
Yeah, there you go. Once we've got that, now it's real similar to the systems we were doing yesterday. You've got a system written like this. If we wanted to use elimination to help us solve, what would I want to do next?
Get rid of bx.
So those are eliminating. What else am I left with?
It would be 11y equals -44.
Yeah, you got it.
And then you divide both sides by 11. It would be y equals -4.
Yeah. Once you've got the system all set up where something eliminates, the rest of this is going to feel like what we did yesterday. It's just this first part here of figuring out what you have to do to get something to eliminate. We've got our y equals -4. Anything else you want to do?
Yes. So then you can put that into either of the equations or both.
Or both. We've got 4 equations now that we could choose from. Does it matter which equation we're using?
Yes. Has to be one of the first two.
And I know what you're thinking. I've recommended you use one of the original 2 because we could have made a mistake multiplying these. These are correct. Like, we did make a mistake multiplying. If you substituted -4 into any of these 4 equations, you should get the same answer. So you can choose any of the 4, but I always recommend using the original ones because we might have said +32 instead of -32, and you'll get a different result if you're using an equation with a mistake in it. So we've got this. You're recommending we use one of the original 2. Which one do you want to use?
I guess the top.
So let's do this. If I substitute in that equation, what's it going to look like?
So it would turn into 4x minus, plus 12.
-3 times -4 gives us that +12 equals -4. What next?
From there, you subtract 12 from both sides.
That's going to leave me with
4x equals -16 divided by 4 on both sides equals -4.
Yep. So final answer?
Is -4 and -4.
Awesome. So this is why we recommend watch the video from yesterday first. Because after this point, it's all just a review of what we did yesterday. Now, what I do want to say is anytime you're multiplying both equations, you're multiplying. So the numbers are going to get bigger. You could solve any of the systems we were solving in yesterday's lesson using this method. Even those ones where like we didn't have to multiply at all, stuff being just eliminated, you could also do this and get the same answer. What I recommend is check to see if there's an easier way first before you multiply both equations and use elimination to solve it. The reason for that is if you're multiplying a system that doesn't really need to be multiplied, you can get some crazy big numbers. There's nothing wrong with that, but I would recommend not making things more difficult than they need to be. So I would always check first to see, well, can I just add or subtract to have something eliminate? No, okay, do I need to multiply one equation? Like, could I just get away with multiplying only one? And if none of that works, then the double multiplication process. How are you feeling about this?
Good.
I should say elimination this is like my favorite thing in algebra. There's just something so fun about adding equations together. I don't know what it is. It's probably just a sign I should be a math teacher, but I don't know. I get really hyped for this lesson, so I'm glad you're here today. The first couple ones I've got here for you, we're not going to actually solve any of these. I just want you to show me how you would set them up to use elimination. So I wish I hadn't erased it. But in that last problem, you had started by telling me we're going to multiply this first equation by 3, the second equation by 4 to eliminate our x's. I should say as well, we didn't have to eliminate the x's. Remember, you had chosen, like, let's eliminate x. We could have instead eliminated our y's. What would I have wanted to multiply by if we wanted to eliminate y instead?
By the bottom one by 3 and the top one by 5.
How does that help us?
Because if you do that, you get negative 15 and then positive 15.
Yep. So from that, maybe you can see there's a lot of different ways you can go about solving this. If we had chosen this instead and eliminated our y's, would we be getting a different answer? Correct. It would be the same final solution point. If we eliminated y's, all it means is that we would have figured out x first instead of figuring out y first. So the order of finding your solution point would be different, but the final solution point would be the same. So all I'm looking for you to do for these first 3 here is show me what you would do to the system to help you eliminate. And I showed that last part to show there are multiple correct answers. So you just have to give me one. Okay?
Okay.
You want to do it on your paper and then I'll hear what you got?
Okay.
And people at home, please do this as well. I feel like this mask is really muffling me today.
Okay.
You got them?
Yeah.
All right. This first one, tell me what you were doing.
You multiply the first one by negative 3 and the bottom one by 5.
Yep. That would work to eliminate your x's. If you wanted to eliminate your y's instead, you could have done a 9 and a 4. You don't have to worry about a negative sign because they're already different signs. For the second one, what did you do?
Did negative 5 on the top one, and then 2 on the bottom one.
So which variable are you eliminating there?
Y.
Yep. If you wanted to go for the x's, if you did that instead, you could have done 5 and negative 3. Those negative signs could also be for either one.
Yeah.
So here you're getting a positive 10y for the first equation. There's nothing wrong with putting it down there. We just need one of them to be negative.
Yeah.
And then the last one?
Did multiply the first one by 7 and the second one by 2.
So you're eliminating the y there. So that would give you a negative 14 and a positive 14. If I wanted to eliminate x instead, what could we multiply by?
Multiply by 10 and negative 4.
10 here and negative 4 here. That would give you a negative 40 and a positive 40. If I want to eliminate x, this would definitely work. There is another pair of numbers you can multiply by. I should say a completely different pair of numbers, not just like changing where the negative sign is.
Maybe like 2 and 5.
Nice. Two. Which way? Here.
That one is 2, and the bottom one's 5.
How does that help?
It changes the top one into, or one would be a negative. So you still like negative
Okay.
2.
Mm-hmm. So that would give us.
Positive 4. Or well, wait, no.
So we're focusing on eliminating the x's. You had given me 10 and 4 before, so we were getting 40 for both of them. I think you.
Oh, so it would be 2 on the bottom and
There.
5 on top.
I was like, I think you have the right idea. Then you could start confusing yourself.
And one would be a negative.
And one would need to be negative. That also works because that would give you a 20 and a 20. To put some math vocabulary to this one here has multiple correct answers. It goes back to what we call the least, let me not do that again. The suspense. Do you know what I'm going to say? The least
Common denominator.
common multiple. But it's related to lowest common denominator. What the least common multiple is if you're counting up by 4s and you're counting up by 10s, what's the smallest number they have in common? Oftentimes you can find that just by doing what we're doing here and switching the numbers. The least common multiple of 3 and 5 is 15. But there's occasions where the smallest number they have in common you can't find it by switching those around. There's a smaller number. So here it would be 20, which is why multiplying by 5 and 2 also works. Now, if we were to multiply by 10 and 4, is that wrong? No. It kind of goes back to what we were saying earlier. If you multiply by 10 and 4 instead of 5 and 2, 10 and 4 is giving you very large numbers. The numbers in this one are already kind of large. But you'll end up getting the same solution point. You feeling good about this?
Yes.
I think you did great. There is one for you to try where you actually are going to solve it now. It's this one here. The question is, at what point do these lines intersect? You have your system. I'm going to have you go ahead and solve it, okay? We said if we wear these, we still have to wear the mask, right? The face shield. Yeah.
It's proven difficult for both of us to get used to that.
Yeah.
I
I feel.
thought it was low, and I felt like I was gonna suffocate.
I feel like this mask is like really muffling me today. Maybe.
It's just that we've gotten used to it.
But I think you're still supposed to wear, if you're wearing a face shield, you still are supposed to have the mask on. But I'm also like 10 feet away from Niall. Maybe I'll ask. I think I'll ask. If they say it's fine, I might, when I'm filming a video, wear this instead of the mask. How you doing? Mm-hmm.
I don't know, this is kind of...
Everything looks good so far. When you're using elimination and you're multiplying both equations, the numbers are going to get large. So I think the only reason it looks weird to you is because you're looking at some big numbers. But everything mathematically is good.
Okay.
You still sound unsure, but everything's good. Mm-hmm. Mm-hmm.
Okay.
What'd you get?
I got 3 and 3.
3 and 3. Okay. And just like for all these systems we've been looking at, we can check our answer by substituting it into our system. If I substitute this for the first equation, what is it going to look like?
We give you 12 plus 21 equals -9. Yeah.
Why are you making that face? Tell me what you're thinking.
Oh wait, no, y is -3.
Y is -3?
Yeah.
So this is a perfect example of why checking is helpful, right? Because we had our answer, we went to check, you're looking at this and you're like, that is not true. That does not make sense. I saw you look down at your work and you said, oh, wait a second, y should be negative. So just by checking, I didn't say a word. I just stood here and asked you why you were making faces. But you were able to figure out your mistake on your own just by doing that. So if I make y -3, how does that change our check?
It would be -21.
Mm-hmm. Does that look better to you?
Yes.
Okay, what about the second one?
You'd get 9 plus 9
Mm-hmm, because the -3 times -3 gives us that +9.
equals 18.
Which equals 18. Yep. So that helps us know our answer is correct. Now, as you were doing the math, I saw you were hesitating because the numbers were getting large, but as soon as you saw, what did you had the x's eliminate, I think?
Mm-hmm.
So when you got that -33, y equals 99, I heard you go, How did you know like you were on the right track?
Because you realize you can divide 33 by
Mm-hmm.
99.
And so you were like, oh, look, it's going to divide nicely. It lets me know I'm doing it right. I do want to ask, do you think when we solve systems, it's always going to be nice numbers like this? No, of course not. I'm specifically choosing systems right now that have these nice, beautiful whole numbers or integers. But there's no reason why I couldn't give you a system where you get like 3.5 or -3.7. You can definitely have systems that have fractions and decimals in them. And when you look at application questions or like word problems that use systems, more often than not, you're going to get some of those fun numbers, just because in life, not everything comes out to be nice whole numbers. How are you feeling on this?
Good.
Okay. There is a second part to this. Remember we said we're going to talk about types of solutions as well. So I've got this system right here for us. This will be a good kind of check to review all the different methods we have. Let's start off by which method do you want to use to solve the system? You could answer with graphing, substitution, or elimination.
Substitution.
Tell me why.
Because you can subtract the top from the bottom.
Subtract the top from the bottom. So you're saying subtract these equations?
I mean, I guess you could do multiplication. You can multiply the top by 2.
Okay. So if we're getting into multiplying equations, which method is that? Is that graphing, substitution, or elimination?
Elimination.
Yeah. Substitution is the method where you need it to either say, you're saying, oh, so you tell me. Substitution.
Substitution is replacing.
Uh-huh.
I don't know why I thought that meant subtraction.
They both sound similar. So for substitution, we would need x equals something or y equals something to replace. Now, I do want to acknowledge, could we use substitution here?
Yes.
It would require a little pre-work, I would say. But that is an option. You could take an equation, you could choose, do I want to solve for x or solve for y, get something, and then substitute it. That is an option. It always is an option. But I would say what you're thinking is if it looks something like this, where all you have to do is go in and multiply one equation and then eliminate, that's probably going to be the one that requires the least amount of work. So I heard you say multiply an equation. Which equation do you want to multiply?
The top one.
Sure. By what number?
2.
How does that help us?
Because you get 4x
Mm-hmm.
and 6y and 24.
Mm-hmm. So we've got that for our first equation. Are we keeping the second equation the same, or do you want to multiply it as well?
Keeping it the same. You could multiply the top one by -2 instead of the 2.
How is that helping us?
Because you need to be able to get rid of something.
Mm-hmm. So if I do that, what am I going to change about that first equation?
It would be -4x minus 6y equals -24.
Yep. What I like is that you went back to what we had talked about yesterday and saw that there's an easier way than multiplying both equations. We can have something eliminate by just multiplying one. I will say, once you had that 2 there, I've also seen people say, let's multiply the first one by 2 and the second one by -1. Would that also work?
Yes.
Yeah, it's just separating the work, I guess. And you went back and you were like, actually, we can just put a negative sign there and be done with it. These are all good options. We've got this system. Is something going to eliminate?
Yes.
What's going to eliminate?
All of it.
Why is all of it going to eliminate?
Because -4x, 4x, 0 cancels out.
Nice.
-6y, 6y cancels out.
And what I liked is I heard you mentioned 0. So when these are canceling out, what that really means is it's giving us a 0 on this side. What about on the other side?
-24 and 24 will give you 0.
More zeros. Okay. So I'm left with 0 equals 0. How is this different than what's happened in all the other systems?
Before you would have one of the variables left.
Mm-hmm. And now we have nothing left. Remember our goal. Our goal has been to write the solution point. So we're trying to figure out what x equals and what y equals. Now sometimes people will see this and be like, okay, well I guess 0 is 0. But this isn't saying x equals 0 or y equals 0. This is saying 0 equals 0. When all of our variables eliminate, cancel out like this, it means I can't write a solution point because I don't know what x is or what y is. This is going to go back to what we talked about with types of solutions. If you remember when we were talking about graphing, solving by graphing, we said there's 3 different options. We said most of the time, those 2 equations are going to intersect at a point, and then there is one solution for that system. And that one solution you would label with a solution point. But there were 2 other options. What was one of the other options?
Substitution. I'm sorry.
One of the options for the system. So one possible option when you graph those two lines is those two lines could intersect at one point. What's another thing you could see when you go to graph?
Infinitely many solutions.
Okay, so that's the answer. What would that graph look like if they have infinitely many solutions?
Both the lines would be on top of each other.
Nice. Infinitely many solutions was when we graphed one line. It was all good. But when you graphed the other line, it was on top of that first line. There's infinitely many solutions because
The lines are on top of each other.
Mhm.
Means they're always intersecting.
yeah. Ooh, I like that. So this one here is intersecting at one point. You're saying they're always intersecting. They're intersecting at all the same points because they are the same line. So that was a second option. What was the last option?
No solution.
What does no solution look like?
0 equals 0.
What did the graph look like for it?
The lines never intersect.
Why would lines never intersect?
If they're parallel.
Nice. Parallel lines. So parallel lines never intersect. The solution point is the intersection point. So if they never intersect, that means there is no solution point or no solution. At this point, we can see there's something different about this one. I can't solve for x or y. It means it's not going to be like this. It's not a solution point. It means it's going to be one of these other options. The way we're going to decide which one it is by looking at what is left over here. We're going to look and see, is it saying something that's true or something that's not true? If it's something that's not true, that means there is no point in no world. Let's say, for example, it said like 10 equals 5. In no world does 10 equals 5. There is no point we could substitute into the system to make 10 equals 5. So if we get something that's not true, it means
No solution.
perfect. If we get something that is true, like it means it doesn't matter which point we're going to substitute into it. It doesn't matter because they're going to end up canceling out and giving you something that's true. So there's a lot of points that would work, which would mean our answer for this is
Infinitely many solutions.
perfect. So these are, in my opinion, really nice because there's not much math we had to do. As soon as we see this, that tells me that this system has infinitely many solutions. Now I want to point out one other thing for this one. Originally when you multiplied this equation by 2 and not -2, do you remember what you got?
The exact same.
The exact same thing. What you saw in that moment is you saw they're the same equation. I literally had over here 4x plus 6y equals 24, 4x plus 6y equals 24. They were the same equation because they're the same line, which is another way to figure out why we're getting infinitely many solutions. If you're ever given a system of the same line twice, it's going to end up working out to be this. Now they might not, upon like first glance, look the same. Like when I look at these two, I think they're different equations until you might multiply by something and see they're actually really the same. How you feeling on this?
Good.
All right. There is this one here. I'm going to leave that over there, I think. Just as a reminder, could I possibly have you do this one on the board? Woo! Thank you all for always being such a good sport about this. I think, those are the new ones. So let's start off with which method are you going to use to solve this?
I guess multiplication again.
So the options are graphing, substitution, or elimination. Those are our 3 methods to solve systems.
Yeah, so elimination.
Tell me why.
Well, I guess you could graph it.
You could graph it. I did not give us a graph here.
Yeah, but there is no graph, so and you can't substitute. Well, substitute?
I don't know. I was about to ask you. I was going to follow up on
Um,
that. So why don't you think you can substitute?
I think you could, or well, because you have to get the x out of the equation.
It doesn't have to be x. You could have x equals something or y equals something to substitute.
Yeah, because it would have to be x or y equals something, but y is by itself.
So if we've got y equals, we can substitute. I am going to go back to something we said earlier. Anytime you've got a system, all three methods could work. I shouldn't say could. All three methods will work. If I gave you graph paper, we could solve this by graphing.
Yeah.
You can solve this by substitution. You can solve this by elimination. Depending on the person, one way might be easier than the other. So if you originally said elimination, if you want to go with elimination, we can do that. But you originally said we can't solve by substitution, and that part I wanted to change. We can solve this by substitution. You don't have to though if you don't want to. You pick what we're doing.
Okay.
You're leading this problem. Which way are you gonna use?
I guess I'll do elimination because I
Okay.
kind of forget substitution
Yeah.
for some reason.
You could always do this one by elimination, and then I'll come back up and do it by substitution. If we want to use elimination. Okay, I like it.
Negative y, is that
Y minus Y?
be negative y? Or will it be nothing?
Nothing. You can always think of it if you want instead of Y minus Y. 1Y minus 1Y gives you nothing.
Mm-hmm. So, does that work?
Mm-hmm.
It
Yeah.
does? So,
So on that left side we've been saying nothing, but what number would that be?
0?
Yep.
So, 0 equals 3.
Mm-hmm.
So, that means no solution?
Mm-hmm. Why no solution?
Because 0 does not equal 3.
I agree. So that final answer we're gonna write down is what you just said, no solution.
Okay. Okay.
So I will take over. I'm gonna use substitution just because he seemed a little hesitant about substitution. And maybe one of you people at home wanted to use substitution. So substitution, we said we need y equal to something. We've got y equals all of this. So I could substitute all of this in for y. When we do that, we get
4x plus 1 equals 4x minus 2.
now, when we go to solve that equation, what could I do to help me solve?
To get one of the 4x's by themselves,
Mm-hmm.
so you can do plus 2 on both sides.
Mm-hmm. That leaves me with 4x plus 3 equals 4x. What else?
And then from there, divide both sides by 4.
We still have x's on both sides. In order to solve, we need your variable only on one side. So we,
Minus 4 on both sides?
minus 4? When I do that, 4x minus 4x.
Cancels out.
So we're left over here with 3. 3 equals 4x minus 4x.
Cancels out.
Which means...
It's 0. Oh.
There we go. So notice I got the same numbers. It's not always necessarily the same numbers, but I as well got 3 equals 0, which is not true. What I didn't see you do is we want to write no solution. The system has no solution. Now I'm just being extra because I'm going to draw a graph as well to point out something. These two equations, I like how you thought graphing because these equations are perfect for graphing, right? They're both in slope-intercept form. If I wanted to graph this first one, that y-intercept is at 1, and then I'm going up 4 over 1. So up 4 over 1. Would be a little easier if I actually had a graph. The second one, I'm starting at
-2.
Yep, -2 for my y-intercept. But look at our slope. Our slope is the same thing. It means slope tells you the direction. So if the slope of this line was 4, it means it's going up 4 over 1. The slope is the same. It means it's doing the same thing. It's going the same direction. I don't know where these points are, but it's going the same direction, which would mean
no solution.
Because the lines are
not intersecting.
And the word for not intersecting lines is
no solution.
What are these lines? What type of lines are these?
Parallel.
There you go. So that's another way you can confirm. I mean, you were saying all the other stuff, but because the lines, if you were to graph them, are parallel, it's another way to see it's no solution. And this has also been a great problem to prove. You really can use any method. Every single one is going to give you the same thing. You did great. This was the last thing I had. There's a box on your notes under that kind of just summarizes the stuff we've been saying. The first line says if both variables cancel out and you're left with 2 equal numbers, so for example 5 equals 5, we're going to answer
is infinitely many solutions.
Yep. Infinitely many. I'm going to abbreviate that. And then if both variables cancel out and you're left with 2 unequal numbers, your answer is?
No solution.
Yep. So just a summary of what you were telling me. You've got problems at the bottom, right?
Yeah.
Okay. I just didn't make a PowerPoint for them, I guess. Okay. If you want to try those, yep, and then we'll be good. And then at home people, if you want to try the homework, I will see you. Goodbye.